Good morning, everyone, or well, morning when I record this at least. My name is Daniel Kastinen, and this is my bed sheet that I found in the closet that I'm using for a green screen. Let's hope it works. Today I'm going to talk about our new meteor analysis pipeline, or head echo analysis pipeline to be precise. So where does meteors come from? Well, it's mostly from these hunks of ice and rock called comets that is wishing around the solar system. When they get too close to the sun, they sublimate and push out these very large and also very beautiful dust trails along their orbit. These, together with asteroids colliding with each other, form what is called the interplanetary meteoroid complex. In other words, all the dust and small pieces of material in the solar system. Our new pipeline allows us to create probability distributions over possible histories a meteoroid that we detected could have had. This allows us, for example, to look into studies how likely it is to have originated from a parent body, such as this one. So the definition of a meteoroid is something like 100 microns to 1 meter in diameter that is moving in interplanetary space. When one of these meteoroids gets perturbed over long periods of time, sooner or later it might collide with the Earth. What happens then is that one of these meteoroids here along this path, it's going to start heating up, and then it's going to start heating up. The atmosphere gets denser, and these have very high velocities. They can the relative to the Earth velocity can be from 10 to 74 kilometers per second. So slamming into the atmospheric constituents really heats this thing up to the point where at first sputtering has a small contribution, but then after that thermal ablation takes over and fragmentation. And what we see is a solid ball of plasma glowing in the atmosphere. It also leaves a trail of ionized gas behind it. This is called a meteor, this phenomena of burning up in the atmosphere. If it survives this journey, it has to be a quite significantly larger rock, and then it enters dark flight and lands on the surface of the Earth. Then it's called a meteorite. So that's those three terms, sort of meteoroid, meteor, meteorite. Now this is a particularly stunning example of a really big meteor, or a bolide as it's called when it's that big. So let's move on to measurements. Since the meteor is first of all, a very dense ball of plasma around the meteoroid, and then a trail of ionized plasma in the atmosphere, radar systems can be used to detect them, which is why we're here at URSI. With interferometric systems, you can not only determine the range and velocity of the target, you can also determine the direction of arrival of these waves and get where on the sky it was, if you have an interferometric system that is capable of that. Our focus has really been high-powered large aperture radars. Here is a list of some of the more important systems that have been used for meteor studies in the past. So we have focused on the Mu and the Panzer radar, where we apply the pipeline. We also hope to apply the open source version of this on ASCA 3D in the future, which will be a very, very important instrument for meteor studies in the future. It's still under construction though. So, the Mu radar. It's located in Shigaraki, Japan, and these 475 antennas are divided into 25 subgroups, with the outer 6 here being asymmetric. This gives this radar significant interferometric capabilities. Here is a photograph of the antenna field of the Pansy radar. However, this picture doesn't really show the actual configuration of the radar, so I included this illustration, which shows the antenna placement and the subgroup division of both the Pansy in blue here and the Mu radar in green. I also left in the MARCI and the 2.5 lambda Jones configuration, which is regularly used for trail echo measurements. On to what we wanted to add to the Mu analysis pipeline and what we have added. So there are several reasons for adding these things to the pipeline. I'm not going to be able to go over all of them. However, we are writing a paper that fully describes the new pipeline and also most of the reasons for all of the additions. So one of the things that we wanted was probability distributions over all the fitted parameters for every event. So instead of getting just a starting velocity, you would get a probability distribution over all possible starting velocities and how likely they are given the data. We also wanted to make sure that the physical models used for fitting are consistent throughout the code, so that the same models are used everywhere and there cannot be physically inconsistent results between different parts of the analysis. Raw data simulation was also a very important part, which I will discuss more later. And using that to validate all the algorithm and characterize their behavior. We also wanted to refactor the code because reinventing the wheel is not good. So in the end, we want to remove all proprietary aspects of it and refactor it in such a way so that we can publish it open source and it can hopefully be useful to other researchers. And finally, we had a long list of improvements that we wanted to do to all of the basic algorithms. Some that we also found while doing our characterization with raw data simulation. For example, the match filtering needed to be able to handle partial codes, which it didn't do. We wanted to improve the event search, for example, to reduce the number of false positives. And also for the Pansy radar, we wanted it to be able to handle the polar mesospheric echoes, so that it wouldn't falsely classify them as meteors. Some radar terminology that I'm going to use. So here we have a radar. It is transmitting here, and the transmission that is sending out is getting further and further away. Up here is the target. It gets reflected. And this pulse doesn't have to be just a plain old pulse. You can encode it. So here it's shifted 180 degrees, here it's not, then it's shifted and shifted again and not. And this way you can encode a binary number onto a radar pulse. The time it takes for transmission, reception, waiting, and then to transmission again is called the interpulse period. And I generally call this entire sequence a IPP. So I'm not going to be able to go into the very nitty-gritty details of how the analysis works, so let's just call it the analysis. You have the raw data here, you pass it through the analysis, and then you get time series of physical parameters. You get those time series by analyzing one of these pulse codes. That's one point in the time series. The next pulse code is the next point in the time series. So how did we get these probability distributions and the expected uncertainties? Well, it turned out that a lot of the ways we tried initially was way too slow. So what we ended up doing was getting a parameter grid of all of these coded radar pulses, and we simulated the raw data for them, the noisy raw data, and then passed this pulse through the analysis and got the expected uncertainties for just one of these pulses with one point on the parameter grid. Then we covered the entire parameter grid and direct Monte Carlo sampled every point in the grid to get the expected uncertainties. Now this grid can't possibly represent all possible meteors we can measure, but we can interpolate pretty well between the points. So when we have measured a real meteor, we input the meteor data into the interpolation function and get out the expected uncertainties for the meteor data. We validated this method by looking at the measured residuals after fitting with the expected residuals after fitting. In the beginning, it actually turned out that we had forgotten to include an error in the phase calibration of the radar, because the phase calibration is not perfect. And when you don't do that, you underestimate the expected error in the direction of arrival estimation. So once we added that, we got them to match up, and we could finally go on to doing the Bayesian parameter estimation. We did this by applying Markov chain Monte Carlo methods, but basically the idea is that using this Markov chain Monte Carlo method, you can create a distribution that represents the probability of which model is most likely given the data. And this leads us to the result. To start off with, I want to show a sort of typical example from the Mu radar. So here in this picture we see a so-called range time intensity plot. So here is sampled or samples in the received coded sequence, and here is pulses on the x-axis. So this block of higher received power is the reflected code on from the meteor head. This also exhibits some nice fragmentation-like behavior with this oscillation. Here we have range, line of sight velocity, azimuth, elevation. Here is also a scatter plot on the ground projection of the trajectory from the azimuth and elevation and range. Here is the height, and here we have the radar cross-section in this lower left corner. So using these parameters, passing them through the interpolation function, we get the uncertainties for all of these points. Then we run the Markov chain Monte Carlo. And here is the probability distribution of possible models that fit. So here we have starting position in x, y, z, the direction in which the meteor was moving in azimuthal coordinates, azimuth and elevation. Here we have the two parameters for the linear velocity that was used. Usually we use an exponential velocity, but for this one we use the linear velocity, or the pipeline picked the linear velocity because the deceleration curve was not well defined in this one. So this results in this kind of 3 sigma distribution of possible models, where we have the mean model here as red. Here we have east versus time, north versus time, up versus time, also Doppler and line of sight velocity versus time. So this line of sight velocity is much more accurate because it's based on phase differences between pulses. And this is just a projected version of this line of sight velocity. So using this probability distribution, we can transfer it to other higher level parameters such as the orbit. So here are the probability histograms over possible orbits that this meteoroid could have had. So this is very interesting for a few future studies that we are planning, looking at hyperbolic events. However, to create a probability distribution over possible histories that this meteoroid could have had, you can't use just this histogram. You have to use the entire distribution over state space. Here I've illustrated this event in Kepler coordinates. Now this distribution was particularly well behaved, but it seems as likely that it's not. Here is another example of a detected meteor by the Mu radar, where the distribution is highly non-Gaussian. One of the things that we have submitted a paper on now is high altitude meteors. So using all of this raw data simulation and the validation and expected uncertainties to really validate the existence of high altitude meteors. So high altitude meteors would be events that lie in this general region that have high ablation, atypical ablation altitudes for their initial velocity. So this clustering here is due to the previous match filtering code not being able to handle partial sequences of transmitted pulse codes. After the update, we ran the new pipeline on all of these, and here are the results. There were also 2 showers, one shower here and one shower here present in this data, but we do have radar meteors confirmed up to 150 kilometers approximately altitude, starting altitude. So, Pansy radar results. Here is an example from the Pansy radar. So again, this is the same layout. We have ground protection, so the interferometry is up and running, all of the match filtering, everything is up and running for the Pansy radar as well. We also have the Markov chain Monte Carlo up and running for this, and it's working. There are still a few kinks we need to work out with the galactic background noise calibration, which I will not go into now. But I managed for this presentation to at least analyze one of the 4-hour campaigns that we've done and reanalyze one of the 24-hour campaigns from the new radar. So here is a side-by-side look on the Panzer radar and the Mu radar in initial velocity, initial altitude diagram. That's all I'm gonna have time for now. But if you're interested in seeing more of this, you can contact me afterwards. So thanks for watching.